All right, let's dive into one of the biggest, well, paradoxes in our entire solar system. We're going to take a trip to Mercury, and let me tell you, this place is a world of insane extremes. Think scorching fire and deep space ice, literally side by side. I mean, how is that even possible? How can the planet closest to the sun also be freezing cold? You'd think, hey, closest to the sun, it's got to be hot all the time, right? Well, that's not quite the full picture. So let's get into the physics behind this wild temperature swing. And when I say swing, I mean it. We're talking about a 1,000 degree Fahrenheit swing. So during the day, the surface can hit a blistering 800 degrees Fahrenheit. Yeah, that's hot enough to melt lead. But then at night, it plunges all the way down to minus 290. That's a difference of over 1,000 degrees Fahrenheit. Seriously, no other planet even comes close to that. Okay, so what is going on here? What's the secret behind this extreme paradox? Well, here's the thing. It's not just one single cause. It's actually this really cool combination of physics, what the planet's made of, and, well, its very strange sense of time. All right, so here's the first thing you need to know, and it's a bit of a curveball. Mercury is not the hottest planet in the solar system. Nope, that title actually belongs to our neighbor, Venus. And that right there is our first major clue. It tells us that just being close to the sun isn't the whole story. So let's get into the first big piece of this puzzle. It's all about what Mercury doesn't have, and that's a real atmosphere. This part is absolutely crucial to understanding what's happening. See, here on Earth, we've got this nice, thick blanket of air that keeps us warm. Mercury, it has something called an exosphere. And honestly, to call it an atmosphere is being generous. It's this super, super thin layer of atoms. So thin, it's pretty much a vacuum. It can't trap heat, it can't move heat around. It does basically nothing. And this really helps put it all in perspective. So, if we stick with that blanket analogy, Earth has a comfy, just right blanket. Venus, it's got this insanely thick, heavy-duty carbon dioxide blanket that traps everything, creating a crazy greenhouse effect. And Mercury? Well, Mercury has no blanket at all. So the second the sun goes down, poof, all that heat just radiates right back out into space, instantly. Okay, so that's the atmosphere, or lack thereof. Now for the second piece of the puzzle, and this one is, well, it's wild. It's Mercury's ridiculously long day. And I'm not talking about a 25-hour day, no. We're talking about a single day that lasts for months. All right, so the physics here is super interesting. Check this out. Mercury spins on its axis once every 59 Earth days. Pretty slow, right? But here's the catch. It's also zipping around the sun really fast. This combo means that for the sun to get back to the exact same spot in the sky, from one sunrise to the next, it takes a whopping 176 Earth days. That's its solar day. So the takeaway here is huge. Any single spot on Mercury is either getting blasted by the sun or frozen in darkness for a very, very long time. And this timeline really drives the point home. Just try to imagine this. You're standing on Mercury. You'd have about 3 months of non-stop scorching sunlight just baking everything around you. And then, that's followed by 3 months of total freezing darkness. There's no quick rotation to even things out like we have on Earth. Yeah, I saw this put perfectly in the source material. The planet has time to fully bake and fully freeze. That's it, right there. That prolonged exposure is the absolute key. The surface gets months to soak up all that energy, and then it gets months to lose it all. Okay, so we've got the missing atmosphere and the super long day. Let's put these pieces together now and look at the full picture. You can almost think of it like a recipe for creating the most extreme temperatures imaginable. Step 1, you start with some intense, up-close solar radiation. Step 2, get rid of that atmospheric blanket completely. Step 3, slow down the planet's rotation so the day-night cycle is just a crawl. And then, for the final touch, you need a very specific kind of surface. And that final ingredient is Mercury's surface. It's just rock and dust, It's not like Earth, where we have huge oceans that are amazing at absorbing and holding on to heat. Mercury has none of that. So the moment the sun sets, that rocky ground just can't retain any warmth. It all just radiates away into the cold of space. So you put all that together, and what do you get? You get the ultimate unregulated planet. It's completely at the mercy of either the sun's full blast or the deep freeze of space. And really, the big thing to remember is this. It's not any one thing. It's the unique combination, this kind of perfect storm of being close to the sun, having no atmosphere to help out, and having that incredibly long day. All those factors working together are what give Mercury the biggest temperature range in the whole solar system. So, you might be asking, why does this matter? Well, for one, it shows us that just being close to a star isn't everything. It's also a pretty stark reminder of just how important our own atmosphere is for keeping our climate stable and, livable. And finally, it answers that riddle we started with. Why Mercury isn't the hottest planet, but it is the one with the biggest, most extreme temperature range. And that kind of leaves us with a pretty wild thought to chew on. Our atmosphere does so much for us, right? It regulates everything. So, what if Earth lost its atmosphere? Would we become the next Mercury? Would our own home turn into a world of fire and ice? It's definitely something to think about.